time to start the workshop. So, welcome. My name is Diego Redondo. I'm the project manager of the RETROFEED project, working on CIRCE. And we are going to have this online technical workshop related with the aluminum and steel industries. So the workshop will be moderated or led by Olga Lysenko from IBL. Olga is is an expert in the IBL Swedish Environment Research Institute. She's electric engineer and modeling of local energy systems with renewable energy sources in IBL. Okay, so she's working in this energy system modeling, the life cycle costing, and also the climate change mitigation activities. So, Olga, welcome and thanks for moderate the workshop. So the floor is yours. You can start with the workshop.
Thank you, Diego. Hello, everyone, and welcome to our workshop toward more efficient aluminum and steel industries. We are excited to have you here, and thank you for the participating. And I would like to start from our agenda. Can we? We designed it to ensure a productive and engaging experience for all participants. Through the workshop, you will have the opportunity to learn more about digital twin in aluminum industry, digital twin in steel industry, and we will share with you the main achievement on aluminum and steel demo sites, and we will try to also answer and all your questions. So, but now let's start from the project presentation, and Roberto, the floor is yours. You muted, Roberto.
Yeah, thank you. Hello, good morning, everyone. My name is Roberto Areval. I work in CIRCE, and I'm in charge of coordinating the technical activities of the project. So I will give just a brief overview of the whole project, and then we go to the technical presentations. So, okay. The main objective of our project is, as you can read here, is to enable the use of an increasingly variable, biobased, and circular feedstock in process industries. And we aim to do this by retrofitting core equipment, by the implementation of advanced monitoring and control system, and providing support to plant operators by means of a DSS. This is a decision support system covering the whole production chain. So RETROFIT is mostly a circular economy project seeking to improve the flexibility in fuel and in feedstock consumption. And this is achieved by retrofitting core equipment of every industry involved, and also by improving monitoring and control by novel sensors, and by the development of a decision support system which is suited for each industry. In some cases, we are also contributing to decarbonization because we are substituting fossil fuels in some industries. So this concept is demonstrated in 5 resource and energy intensive industries, which are in the ceramic, cement, aluminum, steel, and agrochemical sectors. Okay. This slide presents a graphical summary of the project. What we see in the core, in the center of the image, is the core equipment that are very different core equipments. It can be a furnace like in Feno or Asas, or it can be a chemical reactor like in Fertiberia. upwards, we find the conditioning and pretreatment, such as the lacquering, for example, in aluminium sector, or preheating or combustion air. And downwards, we see the finishing processes, like, for example, cooling fluids in the ceramic sector. The core equipment has been modeled by a digital twin in all cases, while the other processes, upwards and downwards, have been modeled by a variety of techniques, including machine learning. These models are incorporated in the DSS, the digital twins and the machine learning models, in the DSS, which also includes other tools to calculate, for example, KRIs, KPIs, production scheduling, prices forecasting, and other features. Together with the novel sensors, these tools will allow to improve the control of the processes at hand. Next one, please. Okay, so this is just a brief summary of each of our demos. Here in ASAS, you can see the retrofitting actions and our goals. In ASAS, all the retrofitting models have been completed, and the development of the models has also been completed, and we already have some preliminary results that indicate that we are achieving our goals in terms of use of scrap and reduction of GHG emissions and reduction of energy consumption. Next one, please. In Feno, the retrofitting has been completed. The development of the models has also been completed. And now the tests with biochar are underway. Next one, please. In the case of Torrecid, this demo has also completed the retrofitting operations. The models has also been completed, and we already have preliminary results that indicate that we are achieving our goals in all the items, in energy and material saving, in optimization of the fuel consumption thanks to the preheating of the air, and also in the reduction of material waste. In Cetil, in the cement sector, we have the retrofitting is currently underway. It will be completed this month, so soon the test will start. We have completed the development of all the models and novel sensors, so this demo will soon also be completed. And finally, in the agrochemical sector in Fertiberia, here a new reactor is going to be installed in the next months, and tests will start. And finally, a brief overview of our goals. As you can see, we have very ambitious goals in terms of energy efficiency, a reduction of GHG emissions and use of fossil fuels, and increase of productivity and reduce OPEX. In the preliminary cases that we already have some results, we are glad to say that we are achieving these goals. So we hope that the same is true for the demos that are completing the retrofitting in the next months. So thank you, and now I leave the presentation to the technical presentation.
Olga, sorry, you are mute.
Yeah, now I'm mute. Yeah.
Hello.
So thank you, Roberta, for the presentation. Yeah, and now is time for digital twin in aluminum industry. Alexandra, please.
Okay, thank you very much. I have the pleasure to present the presentation about digital twin in aluminum industry. I have some problem with changing. Okay, thank you very much. The scope of this presentation is what was our aim, what is digital twin, how this digital twin can be applied in aluminium industry, how to create the digital twin, our case study, Asash melting furnace, some of the results and further steps. Aim of this study is to develop a digital twin of core process equipment in aluminium sector, characterize the behavior of this equipment, analyze possible retrofitting scenarios and the modification of the process conditions, and provide and improved knowledge of the process. Okay, the aluminium industry still faces two main, I don't know why it's changing, two main environmental problems, which are energy consumption and pollutant emission. Of course, aluminium is widely used in such fields as aviation industry, transportation, package industry, and building industries. The global demands for aluminium is estimating to increase to 3 times by the year 2015. Process, I don't know what is changing. Process of aluminium melting has been investigated for the long time. Different fuels, burners, modifications were simulated and tested. However, the further research is still needed to fulfill the requirements of the environmental regulations, reduce non-renewable fuels consumption, pollutant emission, and improve energy efficiency. Just aluminium melting emits almost 7 tons of CO2 per ton of product, which is the most energy consuming part of the aluminium processing. Digital twin has its roots in aerospace engineering. The idea comes from the Apollo program, as it was the first place where the digital twin idea were put into practice. However, it was not called then digital twin. According to American Institute of Aeronautics and Astronautics, a digital twin is a set of virtual information constructs that mimic the structure, context, and behavior of the individual unique physical asset, is dynamically updated with data from the physical twin through its life cycle and informs decisions that realize the value. Possible application of digital twin are anticipating the response of the system, predicting the system failure, developing new technologies such as virtual prototyping. The aims in digital twin development of the aluminium melting furnace are the better process understanding, prediction of furnace behavior at variable condition, and optimize the furnace performance. To understand how the digital twin can be developed, it is necessary to understand what are mathematical and computational foundation for digital twin. What are connections between experiments, simulations, and digital twin? From existing object, we should get data which can be used for physical model development. Then, based on simulation, we can extract the feature for mechanical learning and reduce order model. Digital twin must be validated based on experimental results, and limitation must be defined. The problem is when we are doing virtual prototyping and testing new solution. In our case, it was new burner. Another problem can be when there is lack of sensors which can be used for validation. In such cases, the digital twin can be based only on simulation and engineering experience of similar system. This was the situation in our case. In case of aluminium melting process, the inputs to digital twin are operating conditions such as power of fuel, temperature of air, air to fuel ratio, and oxygen flow, and parameter concerning the composition of feedstock loading to the furnace, such as total mass of aluminium sources, ratio of scraps, and ratio of contamination to scraps. The outputs are the parameters such as temperature, species concentration, and emissions. I don't know what is going on. Temperatures of refractory source and product quality defined, for example, by amount of dross. In our case, digital twin consists of 3 submodels: reduced order model of furnace, model of aluminium melting, and model of dross formation. Why we had to split our digital twin to submodels? The furnace is working in continuous mode, however, with changing operational parameters. But the melting process is a batch process. The feedstock is loaded to furnace and then discharged after melting. The full simulation of the whole process would be too much computationally demanding. Now I shortly say a few words about those submodels. Next slide, please. To analyze the process of aluminium melting furnace, the model was created of this aluminium furnace with 3 different burner heads. All the dimension of the furnace and boundary conditions were in agreement with the real furnace. The model was simulated, including detailed turbulent combustion with heat and mass transfer, including eddy dissipation, turbulent model, and radiative heat transfer, and 3 main reaction of combustion: methane, ethane, and CO2 were included. The simulation were made in ANSYS Fluent software. Based on a series of simulation for different conditions with predefined range, the surface of response were created using ANSYS Twin Builder software. The ROM was created using genetic aggregation algorithm. The goodness of feed is presented next, please. Yes, is presented as correlation of normalized values of observed and predicted output values. Now a few words about melting process. How the combustion process influences the melting process and vice versa. The combustion process, of course, need to deliver heat necessary for aluminium melting. For one batch about 20 tons, we need about 20 gigajoules of energy. But how melting process can influence the combustion process apart from negative heat source of inside the furnace? Aluminium feedstock consists of ingots and scraps. Ingots are quite clear aluminium, but scraps are recycled and can contain up to 5% of contamination, such as paints or oil. When they are inserted into furnace, those contamination are intensively released as volatile organic compounds and are combusted in the furnace. This also increases the dross formation. The dross is byproduct which increase the product quality and efficiency. Melting process of aluminium involves the phase change of the aluminium. It was simulated using the enthalpy method, and the set of ordinary differential equations were, and also to set of this equation were included the release of volatile organic compounds. It was implemented using Modelica and then compiled and integrated into digital twin. Next, please. Due to lack of any model of dross formation that can be applied for assessment of dross amount, it was necessary to carry out some experiments and develop the model based on that. We did these experiments in our laboratory scale macro TGA for different parameters of temperature, oxygen and scrap fraction. And based on that, we obtained some empirical correlation which allows at least to estimate the quality of the product. The comparison between measured and calculated values are presented at this figure below. And this dross model was also implemented in Modelica and integrated to digital twin. Next, please. However, the digital twin was validated only based on CFD results, because the installation of the new sensors at Asash furnace was finished with some delays. Such parameters as fuel flows are measured constantly, but for example, only total amount of air is known during a batch. The results of some operational parameters must be assumed or estimated based of other. Here we can see the comparison between the measured value, the red line, and simulated green line. As we can see, the discrepancies are visible. However, the roof sensor, which is simulated here, is shielded and indicates the temperature changes with a considerable time lag. We can also see here the step change of temperature caused by sudden release of volatile organic compounds and their combustion with added oxygen. Next slide, please. One of the application of digital twin of the Asash furnace was comparison of two burner heads. One was primary burner heads, and the second was burner head designed by STEC. The results from digital twin show what are advantages of the new design. For example, there is less dross formation, which results in better product quality. Other advantage is the much lower NOx emission, even with higher scrap content. That new burner was already installed in the Acer furnace, and preliminary results show, for example, less natural gas consumption and lower NOx emission than in previous burner, which is in good agreement with our results. Next slide, please. The aim of this work was to develop digital twin of melting process. It allows for quick prediction how selected operating condition and feedstock composition results in outlet parameters, temperature, product quality. Those simulations are unsteady and very fast. In our case, digital twin consists of 3 submodels: a reduced order model of furnace developed based on series of CFD simulations, reduced order model of this model was integrated with the model of melting process and dross formation. All submodels exchange necessary data between them, and together with sensors data from industrial plants, it will be included into the decision support system for the plant operation, and it will help them to assess the potential effects of different retrofit options and optimize production process. Thank you for attention.
Thank you, Alexandra, very much for interesting and detailed presentation. And now, Andrea will talk more about digital twin in steel industry. Please, Andrea, floor is yours.
Thank you, Olga. Good morning at all. I am Andrea De Vito from CSM, Centro Sviluppo Materiali. We are in charge to develop the digital twin for the steel industry. Okay, thank you. First of all, I would like to do a brief introduction about the definition of the digital twins. The digital twin is a virtual representation of a physical system, object, or process. It's created by collecting and integrating real-time data from sensor, device, and other sources to create a digital representation on their part that mirrors the physical entity behaviors, characteristics, and status. So the digital twin helps in understanding and predicting how the physical system will behave under various conditions. So with the digital twin, we can simulate and predict different scenario to optimize, and we can also develop the performance or solve the problem of our system. The digital twins includes not only the data-driven representation of the current state, but also the ability to simulate and predict the future state, making it a powerful tools for decision-making and analysis. The digital twin can range from simple mathematical equation to complex equation, data-driven machine learning models. It depends on the specific application and on the complexity of the physical system that we are to represent or duplicate. Next slide, please, Diego. Thank you. So, what are the main objective of the steel industry in the RETROFEED project? The main object of in the steel sector in the RETROFEED project are to replace partially replace the fossil fuel input material, basically coal and natural gas, in the electrical steel making production cycle with both with the biochar derived from biomass and plastic grain. Also, another objective in the RETROFEED project is to replace coal, lime, and scrap with the steel industry residues, and coming from the steel industry the same, and with this similar residues coming from other industrial sectors. For example, the granulated tire. Next slide, please. Thank you. So, with this objective, a digital twin of the electric arc furnace, the EAF plant, has been developed in this project. The digital twin will include a physical of the EAF will include physical models to reproduce the behavior of the EAF scrap melting process, respect to the new burner with the focus on the main process parameter like melting rate, methane addition, and energy consumption. The digital twin has also been used for the offline simulation that will allow to analyze different scenarios to better set up the EAF process according to the new rules for the EAF management. The new rules basic related to the introduction of the new developed injection or burner. Okay, thank you. So, how the digital twin of the EAF it's made on. The EAF, the DT of the EAF is basically an application that represents the melting process of the EAF plant by taking into account the energy and mass balance of the this plant. So in the slide, it is shown that the mass balance scheme of the model on the left with the contribution of all input and output material flow. The material and the gas input from it's possible to see on the left side the scheme of the mass balance with the material and gas input from the different sources, the mass and slag as the main, let me say, output material. On the other side, on the right side, we can see the energy, the scheme of the energy balance models that take into the account the main in the schema, the main input energy of the system that are the chemical and the electrical energy input, basically. The different energy losses that we have in the process, and the outgoing energy represented basically from the slag and tapped steel. Next. Okay, thank you. So to represent in the EAF digital twin the possibility to evaluate the introduction of the new material, plastic material, we have also inserted the possibility to simulate the introduction, and so the contribution of this new material in our mass and energy balance. So starting from the approximate analysis, it is possible now for each new material added the breakdown of the type of the plastic. So in the model, the contribution of each plastic product that mainly are volatile fraction, fixed carbon and ashes has been represented in the model in the schema in this slide. So Basically, the ashes, the flue gas ends in the freeboards. The ashes increase the slug mass and energy, and the fixed carbon ends totally in the steel bath as mass and energy contribution. Thank you. To automatize, so to speed up and to standardize the adjustment procedures, a new routine has been developed to automatize these procedures. So the model has been wrapped into a minimization CP function that minimizes the difference between the measured temperatures coming from the plant and the temperature predicted by the model. This function minimizes this mathematical difference by changing iteratively the physical exchange parameter used as tuning parameters. Thank you. In that slide, we can see the graph showing the process of the automatic adjusting process. In that slide, we can see that starting from the first, let me say, tentative coefficient, the routine, the automatic routine will decrease step over step the difference among the calculated the difference among the measured temperatures and the calculated one. On the right graph, it is possible to see the results of the adjustment showed for a typical heat, in which it's possible to see the input of the model, the main input of the model, that is the electrical power, the green line, that is an input for the model, and also we can see the calculation, the main calculation, the main output of the model, that is the average bath temperature. That is the average temperature of the steel within the furnace. It's possible to see also that in this case also the predicted value of the model, that is the blue line, it quite fit well the measured temperature, that is the red point, and also the trend of the curve. Okay. We have also used the digital twin in our natural utilization. So to explore a new scenario. The biggest advantage of the digital twin is that we can use it to explore a new scenario. The digital twin of DF is so used to explore a new scenario in which raw materials are substituted for the supply of energy and substances to improve the efficiency of the process and at the same time to reduce the global environment impact. With the time of evaluating the impact of the use of plastic in substitution of the methane inside the electric arc furnace, we simulated a new operative scenario. So starting from real operative condition coming from the plant data, the simulation were carried out by progressively converting one burner at a time for replace the plastic instead of the use of methane, having as a target of the simulation the final temperature. As using plastic, the fixed carbon in BAT will increase. We make also the study of another scenario that has an objective to have the same carbon content in the steel bath, reducing progressively the injection of the coal lunches, having so in that new case as a target not only the same tapping temperature, but also the same carbon content in the bath at the end of the heat. Okay. In that slide, we have represented the main difference in the input used these two simulated cases, in which we can see on the left graph the variation in methane flow rate injection. We can see that using plastic, we can reduce, obviously, to reach the same tapped steel temperature. We have to reduce the injection of methane because of the contribution of the plastic of the total heat insertion in the furnace. On the other side, on the graph on the right, it is possible to see the reduction in the carbon injection to have as objective to reach the same carbon content in the steel bath. So it's possible to see that we can also reduce the carbon content. Okay, in this slide we can see the main results of these two new scenarios simulated. It is possible to see that after converting only one burner the natural gas to a plastic material, the carbon content in the steel bath is almost doubled. This is possible to see in the central bar graph. So to reach the composition of no plastic case, the total carbon was almost halved. On the other side, the furnace with the plastic and less carbon showed a saving of about 48 normal cubic meters of methane and 600 kilograms of coal. However, due to the complexity of the process and the variability of the operating condition that we have in the electric arc furnace process, this simulation do not extend to perform some tests on the real plant. Thank you. As a conclusion, we can see that the implementation made within the model, mainly the ability to represent the injection of the plastic material, will indeed give the indication about the energy and the reduction input due to the injection of these materials. In this way, the digital twin will give a timely indication of the overall greenhouse gas emissions reduction due to the reduction of the fuel and electricity and reduction agent, like carbon and anthracite. It is always important to remember that a tool such as a digital twin is very useful for the design and optimization of the operational practice, especially in the case of changes scenarios, plant layout, or new raw materials. However, testing and validation this new practice on the plant requires adequate test campaign, especially in a plant like the EAF, where the dispersion of the operational results due to the great variability of the process is very high. Okay. Thank you for the attention.
Thank you, Andrea, very much.
That's all for my side. Thank you.
For your interesting, exciting presentation. And now Tutku from Asash and Daniel from FENA will share with us the main achievement on aluminium industry, please.
Hello. I will be talking first about the aluminium and steel industries aluminium part of this project. As you know, the project name RETROFIT is coming from retrofitting, which is maintaining competitive and high performance equipments, and FEEDstock, which is alternative feedstock usage and enabling alternative raw materials in the greener and more feasible raw material systems. As you can see in the retrofit project, Asash Port melting furnace, which is a reverberatory furnace, is developed, retrofitted by novel burner development and oxygen injection system development. Also, we can proceed, by the way. Also, we have integrated some new feedstock, which are painted and lacquered scraps. In the aluminum industry, normally we are not able to use this kind of scraps because they causes a lot of greenhouse gas emissions. So these are not allowed to be melted in the melting furnaces. In order to be able to use post-consumer scraps, we need to pre-process them by the lacquering systems in order to be able to create new feedstocks in our furnaces. We have in this retrofit project integrated the lacquering system. We may proceed. In order to carry out these activities, first of all, we have carried out retrofitting actions. IEN has do some CFD analysis about burner heads and oxygen injection systems, and System Technique, which is another machine developer company in Turkey, has developed and designed and developed new burners and new oxygen injection system, which is integrated into Asash existing fourth melting furnace. Also, a lacquering drum system has been developed within the scope of this project in order to sustain alternative feedstocks, and it has integrated. We may proceed. As you see in the left side, the reverberatory melting furnace of Asash has shown. The burner change with novel burners is done with refractory change. We have dismantled old burners and integrate novel burners in the location you see in the below left side image, burners location. We may proceed. Also, with our project partner, System Technique, they have designed a new delacquering system, and it has been integrated to the Asash facilities. Our route followed by the validation of this delacquering system and the new burners with the new alternative feedstock. We may proceed. As you can see, we have produced aluminum billet, which is the output material of the melting and casting processes, which are the target of this project. On the left side, we have a video. Maybe, Diego, we can try to, run it. As you see in the delacquering system, first of all, shredded, painted and lacquered scraps has entered from the bunker to the system, and they are transferred to the delacuring rotary kiln from the conveyor. The rotary kiln rotates with a constant speed and constant temperature in order to carry out delacuring process, which is decoating of these scraps. The decoated scraps are tried lab scale in firstly, and then tried industrial scale productions. In here, you are seeing a melting furnace of Asash, which are in which we have carried out our process trials. You see our extrusion billets here and our slacks after the project. We may proceed. As a result, as Roberto has mentioned at his part of this presentation, these were the goals and the results of our project. You can see resource efficiency, energy efficiency, greenhouse gas emission result, and fossil resource usage results. As it has been stated in Alexandra's presentation part, the low NOx results caused greenhouse gas emissions to be lowered. It has been enhanced by 75% in carbon dioxide emission. Also, as an fossil resource usage, it has been targeted to decrease it 30%, but in this project, we have achieved 19% low natural gas usage, as Alexandra has mentioned in her part of presentation. Besides, we have supplied more resource efficiency than the goal. We have sustained 57% resource efficiency and 18.5% energy efficiency. With respect to these results, I would like to mention of these results, we have also this meant we have also integrated intelligent monitoring and control systems. Also, we have trying to handle decision support system model, and the developed solutions are also tested not only by operators but also by engineers in the cast house department, which are in which they are responsible for integrating this kind of solutions and arranging some casting trials and feedstocks, etc. Thank you all for listening. We can proceed with the steel part.
Hi, good morning. And now I'm gonna present our demo site, which is a steel plant. So I think that we can proceed. So the aim is the substitution of fossil fuel with other materials, other feedstocks, in order to produce energy and to create a proper foaming slag in our electric arc furnace. As you can see in the picture on the left, is our electric arc furnace with a lot of injectors and burners in the lateral side of the furnace. And so we tried several materials in order to produce chemical energy and to inject materials to replace anthracite and to make a foaming slag. In the right part of the slide, we can see our injection system and has been retrofitted in 2 years almost, 2021 and 2022. Which has a capacity of material of over 100 cubic meters with a dispenser of 3 cubic meters that allow us to inject the material in our furnace. And we have a flow rate up to 40 kilograms per minute. Also, it can vary depending on the material. And we have an average annual consumption up to 4,000 of material per year, and it depends, of course, on the material that we are using. We can go on. Now, this is quite the material that we use in this project, and we, of course, we tried both for replacement for burner, but also for the foaming agent. And the main material, those are the material that we tried. We tried polymers, the first attempt, and we made around 100 is the most important thing is that every material has almost a certain percentage of biogenic carbon content. So the polymers, we try to replace, for example, natural gas as burner. Then we have a large number of trials with tire grains as injection in our furnace, and we we injected such a lot of materials, around 2,000 tons. And for example, we had around 6,000 heats where we inject this material in order to replace anthracite to create a proper foaming slag. And another experimental approach that we had is to try a sort of blended polymers with limestone that should create a sort of foaming slag inside our furnace. And we tried several tons of this material. And of course, we had around 25% of biogenic content. And finally, our ultimate aim is to try biochar. And the trials are still ongoing. We tried a few tons from now. We will see how many tons we were going to try, but this is the main advantage of this material is that it contains almost, we can say, 100% of biogenic content. So is all derived from biomass, which has been treated at high temperature with a low oxygen, of course. And we're still ongoing with this material. We can go on. Now I'm gonna show the results of the tire grains, because we had a lot of trials with this material. So we have some results which are statistically valid. So we had large trials both in 2022 and 2023. And we, in this table, I made a comparison between injection and no injection. And the main aspect that we can see is that in 2022, we have a higher substitution rate. And in 2023, we had a lower one, which means that we are going to the reduction, of course, of substitution rate. We are planning to go through one, which is our aim. And because we are knowing more about this material, and we are trying to inject in a better way. And another aspect is that even if we are using or not the ster grain, we are still reducing the anthracite consumption, because it will give the better knowledge on when to use anthracite in our process. This is another important aspect. And I think we can proceed with the. Okay, now this is a part of our project, of course, the DSS, and we use this tool in order to define the best material for both anthracite and natural gas substitution, based, of course, on its availability. And of course, it will give us a huge help in order to know a better knowledge of the flow rate to inject in our furnace, and of course also the timing when to inject this material. And it is able also to give some advantages in order to modify our melting profile in our electric arc furnace plant. So I think that that's all from my side, and thanks.
Thank you very much, Dutko and Daniel, to sharing with us your experience, achievement, and results. So nice results of the project. And now it's time for the questions. I hope that, so feel free to ask any question you would like to know, and our speakers will do their best to provide you the answers and all insights of the project.
Yes, please, you can write it in the chat if you prefer, or if not, you can raise your hand and we'll give you the floor. If there are no, at this moment, we're waiting for the question, but if not, maybe, yeah, we can make some question for the panelists, for the speakers. Right now, just to clarify some points. So I have some questions, for example, for Daniele, for example, that have made the last presentation. So Daniele, you have indicated that you are ongoing with the biochar test, let's say. So I don't know if you have already results, but what result do you think that you are going to obtain, more or less? If you think that, I don't know, you are going to reduce the ratio dark grains or carbon, or I don't know. What do you think are going to be the results?
Yeah, since now we are able to inject only one material per time, of course. So now we are replacing tar grains with our biochar, and we plan to have also several more trials in order to substitute the anthracite. The results, maybe it's too early to, of course, to discuss our results, but it seems to be quite good as an anthracite replacing. But of course, since it's new material, we also have to better understand our handling, our injection system, our dosing, also the flow rate. So it is quite a new material. It is a different material from the previous one that we tried, but we can tell it's almost early, but we can tell that I hope that we will replace anthracite in a certain percentage. I don't know what could be the ratio, of course, because anthracite and biochar are quite different. Seems to be equal, but in real are quite different. And the EAF, of course, will give us response in further trials. So I will, of course, keep you posted about the updates on this topic, of course.
Okay, perfect. Yeah, I understand that. Yeah, it's so early to have good results, and for sure you will need more tests, maybe after the end of the project. So just to know. But in any case, if you can reduce the amount of anthracite that you will use in the electric arc furnace using biochar, I think that at least for the retrofit project will be achieve one of the goals. That is important, but in any case, I think that also for you to have the results for the future, because we don't know if probably it's more expensive than anthracite, but probably in the future will be cheaper, or maybe will be an legislation
we don't know.
obligation. So we don't know, but at least you will have these results. Okay, so perfect, Daniel. Thanks a lot for the
You're welcome.
For the response. So I don't know, Olga, if you want to add something to some of the speakers, or you have some doubt or comment about it, because we don't have any question in the chat.
Yeah, I can. Yeah, that's interesting for me to know about what their vision of the replicability potential of these ideas. So is it possible to do something in the similar industries, or we can could be replica for other industries? What the vision of this case? Maybe someone
Yeah, maybe Tutku, you can. Yeah. So maybe Tutku, you can give a response about the replicability inside your company, even outside.
For aluminum industry, I can answer this question. In Asahi facilities, we are using 4 different melting furnaces, and they are all similar to each other. So since we have integrated new burner solution and new oxygen injection system into the 4th melting furnace in the Asahi site, we can replicate these results, replicate these solutions in our 1st, 2nd, and 3rd furnaces too. Also, the other companies who uses reverberatory type aluminum melting furnace can use this kind of solutions in order to decrease natural gas consumption and get some greenhouse gas emission efficiency. Also, they can use some alternative feedstock solutions as we do. It's not necessary to be the curing system. There are chemical ways, there are some mechanical or thermomechanical ways. In order to sustain more circular environment, I believe that not only aluminum industry, but also all of the energy consumption, more energy consuming industries should know about and should do something about this one.
Thank you. Yeah.
Thank you.
Impressive.
Yeah. And just for example, I have a doubt about, for example, the delacquering system that you are using. You can use the same for the other melting furnaces in your company, or it needed one delacquering system for each of the melting furnace?
At the moment, we haven't integrated this delacquering system any of the furnace. They are working separately.
Okay.
But in the beginning of the project, we have aimed to make the integrated solution. But in this way, it is better because we can use alternative feedstock that we get from the delacquering system in all of the furnaces in Asahi. Not necessary to be an extrusion alloy, but we can try with flat rolled products alloys. So it gives a more production flexibility to us. In the future, the capacity of the delacquering furnace will not be very enough for us because there are more than 4 furnaces in Asahi facilities. So in the future, we need to make a production capacity development projects or integration of new delacquering system project.
Okay, good. So well, in any case, it's good to know that one of the solutions that, in that case, STEC has developed in the project, are very useful for you, and probably in the future you are interested in increase the capacity or have another one in your facility. So, well, also good to know that the things that you are doing in the project are very useful for you. Okay, so that's, I think, that one of the most important things for this kind of projects. Okay, so great. So thanks a lot, Tuku, for the response. Perfect. So and also have a question for Andrea in that case. Well, during your presentation, Andrea, you have indicated that you have made a lot of simulations that are very useful for FENO in that case, but they always need the make real test in their facilities. So I don't know if this is a barrier for you when you are trying to you go to another company and try to explain the benefits of the digital twins or something like that. So I don't know if for the companies it's a barrier to use this kind of digital twin or not, or they think that, okay, we can make digital twin and moreover we are going to make tests that are perfect for us. So I don't know what's your feeling about that.
Yes, Diego. In my opinion, we have no problem in let me say sponsorize and to adapt our model in other plants for other clients, for example, because our model is our digital twin is quite flexible. In the plants that we know we are in touch with also other industrial partners, and in our experience our digital twin is quite flexible and can represent other plants. I don't see any particular limitation. The big limitation that I see is that every time we install this we have to install this digital twin, we have to foresee an adjustment phases forever the good reliability of the results. This is the only one limits, let me say, that I can see. But it's quite natural, For sure, I would like to say that the big amount of data that we received, especially from Feno, for us, it's really good things, because as I can see during my presentation, the EF process is quite variable, so we need a lot of data to have a confidence to say that our results are reliable enough to simulate a new scenario.
Okay.
I don't know if I have.
Yeah, perfect.
Okay.
So I see that you see the other companies, so no, it's not a client, it's a partner for you. So it needs that you are going to work together in order to use the digital twin in the best way. So okay, perfect. So thanks,
Thank you,
Andrea, for
thank
that. Well, Olga, I don't know if you want to ask something to Alexandra about digital twin of that they have provided in the aluminium sector. Do you have any doubt or? Or no? Well, if not, I am a bit aware about the digital twin that they have provided, at least not in the technical aspect, but in another way. So Alexandra, I know that you have, as you know, you have developed the digital twin, and this digital twin is going or has been integrated in the DSS that other partner is performing, that Optit is performing. And I know that you have some troubles to integrate the models. So I don't know if you can explain a bit the reason of these problems. Okay, so I don't know if it's the problem that you have developed three models that are different. So I don't know if the problem is to integrate it in the DSS because there are some communication problems or format problems. So I know that you had some problems, so you can explain a bit to all this. Will be great to know your opinion about that.
Yes, thank you for this question. Yes, at the beginning we had some problems about exchange the data because the FMU compilation made using ANSYS Twin Builder was not able to be read by software which will be the integration of this digital twin with DSS. However, after some communication with ANSYS support, we managed to solve that problem, and I think now we, let's say, the Ayman has or can read our model using their software. However, yes, at the beginning, the compilation of these 3 submodels and then compilation to FMU format caused lots of problem, but after quite a long time, I think finally we solved it.
Okay, perfect. Yeah, I know that. Yeah, let's see. Sometimes it's not only to develop the digital twin, also that you have to integrate to another platform or using another models that are going to integrate. It's an barrier for the development. So it's just something that also, well, other researchers can have in mind or take into account in the future. Okay, so thanks a lot, Alexandra. I don't know if anyone have more questions. They are not questions in the chat. So I don't know, Olga, if you want to add something, or maybe we can finish here the meeting or the workshop.
Yeah, maybe. I don't have any questions. Yeah.
Okay. Yeah, I think that all the partners have explained very well the activities, showing the results, the very good results and development. So, well, thanks a lot thanks to all the speakers to explain the developments, and thanks to all the audience for being there. So we are going to finish here the workshop, and we will share this record with all the registers, and also with all the people that can join to our social media or to our website. Okay, so yes, here you have the website of the project, our social media channels, and also the emails of the people that have told today. So if you have any doubt or any question, you can ask them directly to give you some explanation of about the topics that we have addressed today. Okay, so thanks a lot for your time, and see you in the next research workshop. Okay, bye bye.
Bye.
Thank you.
Thank you. Bye.
Thank you. Bye bye.
Bye, Diego. Thank you.
Bye-bye.
Bye.